Hello everyone, I'm Inho who will be presenting error as signals, stiffness-aware diffusion sampling via embedded Runge-Kutta guidance. As we know, generating data in diffusion model is essentially serving an ODE. During this integration process, we encounter two main types of errors, model-induced error and solver-induced error. While popular guidance methods like CFG or Autoguidance focus purely on reducing model-induced error, leveraging the discrepancy between two different models, they overlook the solver-induced error. In this work, we introduce ERK-Guide, a method that directly targets the solver-induced error. To intuitively understand when the solver-induced error occur, let's look at this sample 2D drift vector field. If you look closely, there are areas where the drip direction changes smoothly. We call this a non-steep region. In contrast, there are areas where the direction changes very rapidly. We call this a steep region. In ODEs, we quantify this degree of rapid change as steepness. When the sampling trajectory passes through these steep regions, standard numerical solvers simply cannot keep up with the sudden changes. This inability to adapt naturally leads to a massive surge in local truncation error, LTE. But what does this error actually looks like? Interestingly, we observed that in steep regions, the LTE aligns almost perfectly with the dominant eigenvector of the local Jacobian. We also provide theoretical insight for this in our paper. This gives us a clear strategy. We can use this dominant eigenvector direction as a proxy to correct the solver-induced error when stiffness is sufficiently high. However, calculating the exact stiffness and eigenvector is far too inefficient for practical sampling. To solve this, we reverse embedded Runge-Kutta or ERK pairs. Simply put, an ERK pair combines two solvers of different orders. For instance, while computing the second-order Wien solution, the first-order Euler solution is naturally generated by a byproduct. By analyzing the difference between these two solutions, we can estimate both values completely for free, without any extra network evaluation. Here is our final guidance formulation. Notice that it works similarly to conventional guidance by extrapolating difference, but it uses distinct solver state instead of different models. Also, our adaptive scaling factor gamma ensures stability by activating only when the stiffness is high. This guidance equation is derived from the exact LTE formula, so please refer to our paper for the detailed mathematical derivation. Now for experiments. First, we verified our cost-free estimators. As shown here, they show a strong correlation with the exactness obtained from JVP method and closely aligned with the dominant eigenvector when stiffness is sufficiently high. This proves our estimators are hierarchical. As a result, ERK-Guide consistently improves sample quality, especially at lower sampling steps when solver-induced error dominate. Furthermore, it seamlessly integrates with conventional guidance methods like CFG and various numerical solvers like the PM solver, and boosting performance even further. Additionally, ERK-Guide is far more effective than conventional adaptive step size methods. And crucially, it introduced minimal time overhead and maintained the exact same memory footprint since it doesn't require additional model evaluation. Finally, the qualitative result confirmed these improvements visually. Compared to the baseline solver, ERK-Guide effectively reduced structural distortion and preserved much finer details in the generated image. To wrap up, here are the three main takeaways from our work. First, we turn a problem into a solution. In steep regions, the solver makes large errors, but those errors strictly point in a specific direction. We simply use this clear direction as a hint to correct the sampling. Second, we got this hint for free. Finding this exact direction is usually too expensive, but by simply comparing the two solver solutions, we estimate this direction without any extra cost. Finally, we demonstrated that ERK-Guide consistently improve image quality when simply applied to conventional solvers or guidance methods. Thank you for listening. For more details, please check out our paper and our code on GitHub.